Like any good workout, I like to finish with a little bit of core. Core is really what stabilizes your entire body. It's really what connects everything. And speaking of connections, let's try to connect everything we learned today and apply it to some of the stuff we learned previously. Right? So that's what we're going to do in example 2. We're going to take what we learned in example 1 and with this bending stress, but then we're going to apply it to a real life beam situation in which we're going to have to solve for the moment diagram. Go ahead and check it out.
Whew. I'm enjoying all this analysis stuff on beams and figuring out bending stress. I hope you are too. Let's get to example 2 and see if we can put all this together. So in example 2, we have a beam with just a general load on it, and we're asked to calculate the maximum bending stress in this beam and draw the qualitative deflected shape. Then we're asked to check if the yield stress, the calculated stress exceeds the yield stress of the material. So what is that bending stress equation again? Well, it's my over I. Sigma equals my over I. So basically we have the same kind of basic setup for bending stress. Let's take a look, right? We don't know sigma. We don't really know the moment at this point, right? So last problem, example 1, we were given a moment. But in this case, we don't know the moment, but we have the loads. So the moment, M, is going to be the max moment that we get from our moment diagram. Y is given to us. We were told that we're going to use the cross-section from example 1. So Y is 9.25 inches and I is 1167.4 inches to the fourth. So go back to example 1 if you have any questions on where these numbers came from. All right, so that basically just means the only thing different here that we have to do is we need to first calculate the moment diagram to find M. Once we do that, we can figure out what the bending stress is. So how do we figure out what the max moment is? Well, we just have to walk through our steps of drawing moment diagrams. So hopefully you paid attention in lesson 14. If not, go back to those videos. But we're just going to go through and draw the moment diagram for a very general load here now. All right, so how do we get started on this moment diagram? Well, like all good things, we start with equilibrium. So we're going to have to figure out let's draw our free body diagram. Free body diagram with forces, so I add AY, BY, and AX. And then I'm going to do my equilibrium equations using that free body diagram. So free body diagrams start us off, and then we do equilibrium equations, the good old 1-2 punch. It's going to get us get these beams whipped into shape. So our equilibrium equations, right? We start some force in the x. Don't forget this. I always like to put this ax equals 0. It's just a good reminder, a good check. Some force in the y, we look at our free body diagram. We have ay plus by. We have a minus 50 kips. And then we have a minus, and we see we have a distributed load. So we're going to need to get the resultant force for that distributed load, the statically equivalent resultant force. So I'll go ahead and sketch that in as R. So in my sum forces equation, I'm just going to put in that value as R. Now R, of course, acts at the center of gravity for this shape. So that little rectangle, the center of gravity is 5 foot from either side. And we're going to have to figure out what that value R is. R, of course, is the area under the curve, so I'm going to call that A1. So this is just the first area. We're going to have a lot of areas if you remember back from how I sketched the shear moment diagrams by the method of inspection. I just kind of tabulate areas on my page that I'm going to use to draw the shear moment diagram. So this first area is going to be 6 kips per feet times 10 feet, so that's a total of 60 kips, and that is what R is in the equation. Now I can't solve for AY and BY yet, so I need to move on to sum moments. And so now I'm going to sum moments. I sum moments about point A. So my first term is BY times 20 feet. Then I have the 50 kips times a distance of 15 feet, and then that's going to be negative because it causes clockwise rotation relative to point A. And then I have minus r times 5 feet equals 0. Alright, so from this I can now solve for by. I do the math. By is 52.5 kips, and that'll be acting up. Now I'm just going to take my result for by and plug it back into my sum forces in the y equation. And so when I do that, I get by is now 52.5 kips, so now I can solve for ay. Ay is a total of 57.5 kips, also acting upward. Alright, with this information, I'm ready to draw my shear diagram. So let me kind of zoom in a little bit so you can see this a little bit clearer. Alright, so just kind of label my shear. I start at 0, and then I immediately jump up from the point load AY. So I jump up a value of AY, or 57.5 kips up. So that arrow pushes my shear diagram. Think of the arrows pushing your shear diagram. AY pushes my shear diagram up 57.5 kips. Now I have that distributed load. My distributed load is gradually pushing my shear diagram back down. Now over the entire range of that 10 feet, it goes down a total of 60 kips, or the value of A1. So 57.5 kips minus 60 gives us negative 2.5 kips. And because that's a constant distributed load, when I take the integral of that, I get a linear function, so my shear changes linearly. From 10 to 15, nothing really changes. And then at 15, I drop 50, so negative 2.5 minus 50 gives me negative 52.5 kips. And then I get to by, and that pushes my shear diagram back up to 0. Let me add my sign convention in here for my shear diagram, and I now have the shear complete. Now we didn't really need the shear diagram to solve this problem, except we need to know what the max moment is. So we're going to use the shear diagram now to calculate the max moment. We know that where the maximum on our moment diagram, maximum or minimum value on our moment diagram, corresponds to any time that the shear is 0. So that's going to be an important point. So I've kind of drawn a line down in blue, and I need to identify this value x. So whenever you have kind of this linear change, you can just use similar triangles to solve for x. So I'm going to use the height of this blue triangle and the base of this blue triangle. So I'm going to say that the height, 57.5 kips over x, has to be similar to the height of this orange triangle over the base of the orange triangle. Now the height of the orange triangle is a total drop of A1, or 60 kips, and the base of that is the entire length of that range, which is 10 feet. So now I can solve for x just from this proportion, and so now I get that x has to be equal to 9.583 feet. Alright, so now that I have that distance, I'm ready to go ahead and knock out a bunch of areas for the shear diagram. So first I'll take this area in blue, I'll call this A2. A2 will be 1/2 the base times the height, and I'm just going to delete that orange so it doesn't confuse you. So 1/2 the base, which is 9.583 feet, and the height, which is 57.5 kips. And then I do some math there, and that tells me A2 is equal to 275.52 kips times feet. Okay, now I'm going to finish drawing the whole moment diagram. So now I need that little tiny orange triangle that I just drew in there. That's going to be area 3. Area 3 is going to be 1/2 the base times the height, just like the area for any triangle. So it's going to be 1/2 the base. Now the base is going to be 10 feet minus x, or just 10 minus x, and the height is negative 2.5 kips. Okay, again, I keep that negative around just because it's going to tell me the change in my moment diagram. So this is minus 0.52 kip feet. I'm going to just knock out the rest of the areas for my shear diagram before I even try to draw my moment diagram. So area 4, I'll shade in green. Looks like I called that area 3 by mistake again. I'm sorry. So area 3 in green is minus 2.5 kips times 5 feet, or negative 12.5 kip feet. And now I need to get the final one. I'll shade this in magenta. That's going to be what I now have as A4. Sorry, I have two A3s there, folks. A4 is going to be negative 52.5 kips times the distance, 5 feet, for a total of negative 262.5 kip feet. All right, now that I have all my areas calculated, it's just a matter of going through and following my rules to draw my moment diagram. So I start at the end of the beam and add a pin, so my moment starts at 0. From 0 to the blue line, or over that distance x, I change a value of A2, which is 275.52 kip feet. Again, initially I have high changes in area, then I have low changes, so it's a parabola, and it's a parabola that is concave down. Then, over the next range, that next little segment, I drop minus 0.52 kip feet, and then that's still concave down, so 275.52 minus 5.2, minus 0.52 gives us just 275 kip feet. Over the next range, I drop negative 12.5 kip feet. I'll try to draw this in as a straight line. I'll see if I can figure that how to do that on the in this program. But basically, 275 minus 12.5 kip feet gives us 262.5 kip feet. There we go, straight line. And then on the last range, 262.5 plus the magenta area, which is minus 262.5, brings me back down to 0. I'm happy because I got back down to 0. So that's good news for my moment diagram. That typically means I did it correctly. And I went ahead and draw my positive sign convention. All right, so there you go. You got the moment diagram done. Now, again, this is just one of the steps to this problem. The problem is asking for bending stress, not the moment diagram. So we need to remember that. Let's head back up to that bending stress equation. That bending stress equation is my over I. And now we know that M max is 275.52 kip feet. So now I'm going to plug that in to my bending stress equation. Again, since I is in inches to the fourth and y is in inches, I need to convert this into inches, kip times inches. So just make sure we stay on top of our conversions. And then I plug in y and I plug in I on the bottom. And then we just do the calculations and we solve that the stress here is equal to 26.28 KSI, or kips per square inch. The question asks us, does this calculated stress exceed the yield stress? Does 26.28 KSI exceed the yield stress of 50 KSI? That would be a no, it does not. So, kind of ran out of room on this paper, so I'll just kind of super zoom in and squeeze this in there. No, the calculated stress does not exceed the yield stress of the material. All right, the very last part, looking back through the equation, says to draw the qualitative deflected shape. I really like the little shape of the moment diagram. You can easily see from that moment diagram that the top is in compression and the bottom is in tension. So that's easy to figure out, like, you know, in terms of our stress, our bending stress. We know at the top of the cross section we have compression, bottom is in tension. It also tells us about the deflected shape. So if I sketch in my supports where I know I have to have zero deflection, I then know that I have to have a concave up beam, a smiley face beam, and that would be something along the lines like this. Now, because my moment is a little bit higher towards the left, I've given in the beam a little bit more deflection. Now, you know, the max moment doesn't necessarily coincide with the max deflection, but, you know, it'll be closer to the left-hand side of the beam than to the right. All right, it's been a great lesson. I'll talk to you later.